We have 3 presentations more, and the next is by Samuel Brown, who is at the Department of Polymers and Coatings, and he will make another presentation on metal nanoclusters and their optical properties.
Yes.
Floor is yours.
As you mentioned, I'll be exploring the oxidation states for optically active silver nanoclusters. So to begin with, I'm just going to describe silver at different length scales. So here you can see we have silver in the bulk, just a silver metal block. And then this, if you look, is a TEM image of a silver nanoparticle that's about 6 nanometers in diameter. And then here's the model that we'll be working with later, a silver nanocluster that's only 13 atoms total. And then here's the representative density of states for each one of these models. So just kind of for reference of what we'll be looking at. So because the density of states becomes discretized for the smaller nanocrystals, that allows for different optical transitions. And then work by Diaz and Ross showed that, one of the papers showed that you can actually get fluorescence from these models. And then with the nanoparticles that are slightly bigger, you can get surface plasmon resonance, which alters the absorbance properties. In this presentation, though, we'll be focusing mainly on the silver nano clusters, the very small ones that can be optically active. So here's a molecular dynamics room temperature of the model that we'll be going over. So it's a silver nanocluster with 13 atoms making up the core of the silver, and then it's passivated with 12 cytosine molecules. So typically when they synthesize these in the lab, they use DNA as a scaffolding material. So for this case, we're using cytosine as the representative scaffolding. So what we wanted to do first was just explore the different oxidation states and charges of the system to see if we can find a lowest energy. And when we did that, we found that the lowest energy was at a charge about -500, which is extremely low. So we decided to kind of explore a different area. So we went and looked at the charges around the neutral state. And looking at this, we can see that we get a deviation from the parabolic function we saw earlier to a quadratic function here with a inflection point around -6. This inflection point doesn't give us a whole lot. I looked at density states around it, and it seems to be similar, but looking at these models, we then explored the band gap for these ones, which is here. So I didn't mention we looked at different spins of 0, 1, 2, and 3. So this is spin 0, 1, 2, and 3. And then we looked at the band gap for all these different oxidation states. And for high oxidation states from about 3 to 10 in these models, we can see that the band gap considerably widens to about 2 eV. And since we did this for both alpha and beta electrons, we multiplied the band gap of the beta electrons by -1, so that's why we have a negative band gap here. Looking at the models that were optically active and had a band gap in the previous one, we then we plotted the band gap, the HOMO-LUMO energy for these different states, which is here. So you can see for a higher oxidation states, +11 compared to +5, that both the HOMO and LUMO energy drop, and that's pretty much independent of the spin of the system. So for now, we're just going to look, in the interest of time, at these two different spin states, the optically active systems where both the alpha and beta electrons both have band gaps. So looking at the density states of these systems, you can see that, as we'd expect, all the electrons are within the conduction or the valence band, and where if you excited it, they would jump into the conduction band, and you'd expect to see some sort of fluorescence or something like that. And then if you increase the charge, so you're increasing or decreasing the number of electrons, you lose states. So that's why it looks like it's more discretized in these cases. So we're now going to look at some of the optical properties, absorbance, and some of the different molecular orbitals for just this specific model. So looking at this, we determined the oscillator strengths for that, and using this equation here, we can develop an absorption spectra using these oscillator strengths, which is what we have here. And these vertical lines indicate the 4 strongest oscillator strengths, so the 4 most probable transitions, which are also listed here. So looking at these, the molecular orbitals of these 4 strongest transitions, we see that for all the lower energy states, so this is where the electron would first preside before it is excited, that all molecular orbital resides right around the core of the silver. But But then when we excite it, it jumps to a molecular orbital that resides predominantly on the ligand. So this kind of gives us an idea that not only is the size of these silver nanoclusters and the charge important to the photophysical properties, but the ligand itself is also plays a role in the fluorescence. So just a quick conclusion. We have a silver nanoparticle. We looked at the different energy and we found the minimum to be around -500. But then we looked further near neutral states. We saw that several of these would have a band gap open up, and then we looked at it and found that the ligand played a critical role in the fluorescence. So
let's thank Sam for. And questions are welcome if. Yes.
I interrupt you right away.
Yeah.
Do you know the structure? Is it known experimentally for that it's really setting atoms in the silver, and also what the conformation silver has? Is it experimentally known, or you just took this structure because you need some to start?
Something just to start with.
Okay, so no experimental data on this.
Yeah.
Okay.
Just a
So quick question, in one slide you saw that the charge is something like 500 or something. What do you mean? So you start with then you dump in 500 electron into the.
Yep, that's what we just put in a bunch of electrons. So
That's a huge number.
So I first started out just why I did that. I started around here and I got this and I thought that it would kind of come back up in a parabolic. So I wanted to try to find that minimum energy. And as I kept going, it kept going down until I just started dumping in tons of electrons. So I found the minimum, but is it physically relevant? Not really. So it's just kind of what it is.
Okay, let's thank Sam once again. Center is Aaron Fordev, who is also in MNT
10 minutes.
program.
20 minutes.
You better plan to finish 10 minutes. And I suggest that we make a group photo before leaving, after all presentations. So he will be telling about new materials which are becoming famous and favorite for photovoltaics, so-called lead halide perovskites. Floor is yours.
Hello everyone, my name is Aaron Fordy, and for the next couple of years my research will be involved looking at the charge transfer states for photoexcited transitions. So for my project I decided to look at the charge transfer states between lead halide perovskite and organic dye molecule. So motivation, so why lead halide perovskite? So the biggest motivation is it shows a lot of promise for next generation photovoltaics for like dye synthesized solar cells and thin films due to its well-aligned band gap, its high absorption of visible light, and its ability to transfer charge carriers long distances. So since it can carry charge carriers long distances, it can act as either an electron transport material or a hole transport material as well. So it's pretty versatile in that way. So then what we need to do is we need to find molecules to pair with it to extract either the electron or the hole out of it to do spatial separation of the charges so that we can run them through the circuits of the solar cells to get power. So for the models I use, specifically I use cesium lead iodine perovskite, CSPBI3. And then for the organic dye molecule, I just chose triphenyl nitrogen because it's the simplest dye molecule I could look at to begin with. And then for the input atomistic model for VASP, I chose a CSA-PB8I24 slab. So it's a couple unit cells that has a surface and then it extends periodically into the structure to mimic bulk characteristics. And then we just place the dye molecule. It's not physically connected, it's just placed pretty close to the surface of the perovskite. And just to know that all of these conclusions, they were done at a ground state optimization, so it's all 0K, so there's no thermal fluctuations with these results here. So if we're looking at the spatial distribution of electronic charges, the right table shows the electronic transitions between orbitals I and J, so HOMO -2 to LUMO +8 state, and then the oscillator strengths for that transition, which gives the probability of that transition occurring, and then the transition energies, those transitions. So for this first one here, for the HOMO -2 to the LUMO +8, we can see that there's not much spatial charge separation because it's basically just jumps into another region of the perovskite. And that kind of makes sense that it has a high probability, because when you look at the oscillator strength, it comes from the transition dipole, which is the oscillator strength is proportional to the square of the transition dipole. And the transition dipole is basically a measure of the orbital overlap between transition states. So it makes sense that the highest probability one would be spatially close regions for transitions. But then, if we look at states that do produce spatial separation of charges, like our HOMO and LUMO state here, where the electron would reside on the perovskite and the hole would reside on the HOMO, we see we do get charge separation there, but it has a very low probability of occurring due to there's not much spatial overlap between the orbitals. They're on different sides of the materials, basically. So, to summarize that, the most probable photo-induced electronic transitions occur within the perovskite, and they don't produce charge separation. While the transitions that do result in spatially separated charges, they have a very low probability of occurring. So we have to consider a different method to get spatially separated charges. So on the left, this shows the photoexcitation from the HOMO -2 state, which leaves a hole, to the LUMO +8 state where the electron would reside. And then if you think about it, that this is a very unstable state, and then the electron will want to come back down and try to get into equilibrium. And to do that, it will relax to the band edges, which happens approximately on the picosecond level. So if both electron and the hole come to the band gaps, that will produce spatially separated charges. So to show this conclusively, I would have to do the charge transfer dynamics of this system as a next project to follow up on this. So in conclusion, photo-induced electronic transitions themselves are not enough to generate charge separation. We need to consider the relaxation processes after the photoexcitation to the HOMO and LUMO gaps, where the electron would reside on the perovskite and the hole would be on the organic dye. So the organic dye acts basically as a hole transfer material. And then as a bonus, just a little simulation. As you can see, like the organic dye is it moves around a lot, and then the perovskite is very heavy, and if you look close enough, you can see some of the modes that move. And then for the next iteration as well, we would bind that molecule, place some functional groups on it, and bind it to the surface.
Okay, thank you, Aaron. So, questions?
What exactly is the purpose of getting this molecule on the surface of perovskite? I completely miss your motivation, because perovskites are known to be used just by itself, right? And getting right away 20% efficiency in solar cells, right? Means it's already providing the charge separation without any additional molecules on the surface or anything. What exactly is the purpose of getting this molecule on the surface of perovskite?
Okay,
what is exactly your motivation?
The literature I've seen is that the perovskite, it can act as itself to separate charges. It has an internal electric field, but that's for methyl ammonium, which with the internal cation, it can create internal electric fields. But for cesium, it's just a charge.
Oh, and yours was not lead, it was cesium?
It's lead, but it's cesium. So if you look at for other, the methyl ammonium in the middle, and this one's just a cesium, so it's just a static charge, where with the methyl ammonium, it can create internal electric fields.
Okay.
So for this one enough, it wouldn't create internal electric fields to separate the charges.
So you modify the lattice of your perovskite, kind of taking the molecule which is known that it's not very ligand, which is not very favorable in terms of charge separation, right? Mm-hmm. And you trying to improve this charge separation?
In solar cells.
Silicon.
Or you need an interface.
You need some sort of interface to produce the electric field to separate the charges.
Can you make connections to this?
So in this case, even though the cesium is charged, it doesn't create an electric field like the methyl ammonium would, because they can rotate and it can create little ferroelectric highways for the charges to kind of separate. So in this one, there's no net internal electric field to separate the charges. So we need another molecule to pull one of the charges away.
But other type of perovskites exist where this internal field is good to have, right? Just because you having the right ligands there. Am I right? Mm-hmm. And these perovskites have been shown really good promise for the solar cells. The question is, what exactly the benefits would be to take these other ligands?
Would you comment on this?
Yeah, so you need to separate the charges before they can migrate to the electrodes. So like if you see here, like if you just separate these two charges, they're gonna want to come back together instead of separate.
So you want to remove charge from your perovskite?
Yes.
Somewhere away. Selectively remove which charge, positive or negative?
Either one, as long as.
But here, in your work, which
here the hole
charge
was
are you?
taken up.
Huh?
And here the hole was taken.
So you're removing positive charge.
Yes.
Only. Okay. There was very briefly.
Yeah, that's almost same question. Now, what's the direction of the charge flow? Is going towards the dye, or when you're separating hole and electron, right?
Yeah.
What is the direction of the hole? And
So this would be the hole, because if you photoexcite an electron, it's going to be above the band gap. So when it comes back down, it's going to be on the LUMO. And the LUMO's
you
out.
said they are not physically connected. I mean, they are not bonded. So what's the mechanism of charge transferring to, or hole transfer towards the? What is the direction of the hole? And
So this would be the hole, because if you photoexcite an electron, it's going to be above the band gap. So when it comes back down, it's going to be on the LUMO. And the LUMO's
you
out.
said they are not physically connected. I mean, they are not bonded. So what's the mechanism of charge transferring to, or hole transfer towards the?
Right, this one's not going to be the most physically active, but you can kind of see they're close enough where you can get some sort of tunneling between the
And
charges.
how can you move the hole to that?
Oh,
dye?
then this would be connected to another dye molecule. This is just a short segment of a dye molecule, but in reality they're bigger organic molecules, so it'll transfer through that molecule, and it's going to take the least conductive route, so it'll just keep going through the molecule to get to the electrode.
Good. Let's thank Aaron and all audience for the discussion. And we have last presentation by Levi Blustrom, who will continue the same area of research, the photoinduced charge transfer at the interface of inorganic and organic materials with some specifics and some interesting analysis.
Okay. Thank you all for sticking around. Today I'm going to talk about two different dyes and the rate at which holes will be taken from the quantum dot. So the motivation behind my talk is we want to put it inside of a solar cell, and there's several things that need to occur. But the things that I'm interested in are the rates at which the electron is taken from the quantum dot and the hole. And we want the whole rate to be faster than the electron because that helps the system be more efficient. So to do that, we want to try and find ligands that will extract the whole from the quantum dot. And there was a paper by the Weiss's group where they took the same acceptor and they linked it through two different linkage groups, one being PTC and one being BA, and I'll just say the first one, not the entire name. And PTC has been shown to very well interact and couple with the quantum dot, and it makes the absorption spectra redshift, and you can kind of think of that as the particle in a box. The box has got slightly bigger because it interacts with the sulfur on the group.
And again, what's the difference between your linkage just because so small?
Oh, sorry. So it's sulfur for PTC and oxygen for DMA. So
it's carboxylate and the
yeah.
sulfate group.
Yeah, so that's the only thing that's different, is the oxygen and sulfur. So this is my system. I have a totally neutral, so I have 33 cadmium selenium quantum dot, and then I have my full ligand with an extra cadmium, and then I took a reduced model of the ligand to keep it charge neutral, because these systems typically are charge neutral, and we don't want the charges to close the band gap. So the methodology, just like everyone else, I use VASP with GGA, functional PBE, and my main tool in this is when we collapse the CHEM orbitals into either one dimension or just, two dimensions. So we have z and then the amplitude, or just the center of mass. And that's given by these equations. So in the experiment, they excite at 2.95 electron volts. And if we look at the states that are important around that region, we can already see the difference where for the PTC, we have some states that are very charge transfer in nature, which would mean that we already broke our exciton into the electron and hole, so then the hole can be extracted very easily. But for the BA, none of the states are that charge transfer. And how we get this is if we look at our, this is the different states, and then plot the center of mass, and we can see here that there's, it's localized on the ligand, and then everywhere else on top is localized on the quantum dot. And we can see that a lot of the PTC are excited, the hole is in this region. So the BA has to relax down to almost a HOMO level to be able to get a charge transfer state. So this is very important because we want to see charge transfer. So from this diagram, we can make a conclusion that PTC facilitates charge transfer because it's either initially excited to a charge transfer state, or it has very few states to relax to get to a charge transfer state, where BA, it has to relax almost to the HOMO level. So then this is just a partial charge density of highest charge transfer state. So this is 353, and we can see that the charge transfer is only on the ligand, and there's no localization of the hole on the quantum dot. So in conclusion, we can conclude that PTC facilitates charge transfer because it is either initially excited to a charge transfer state, or it is very close to a charge transfer state, where BA has to relax down to a charge transfer state, which will increase our rate for hole extraction.
Okay, let's thank Levi for presentation, and his presentation is open for discussion and questions.
Yes.
Yes?
Okay. How did you create a quantum dot? I mean, not really a quantum dot. It's more like an atomic cluster. Maybe quite small. But
So for these, back in I think around 2010, there was a paper that described ultra small quantum dots, and the most stable was 34, 34, or 33, 33. So these are experimentally available. And how I did it was I took bulk cadmium selenide in the Wurtzite crystal lattice, and I cut a sphere, and then optimized it.
you started optimization, no MD simulation. No.
Yeah. So I took a already optimized quantum dot because in my research I used quantum dots, so I already had it optimized. So I didn't start from bulk and then have it optimized.
More questions?
So you're saying that you excite to the state which is more energy transfer character?
Yes.
But if it is energy transfer character, then its intensity is probably not as high as just pure quantum dot transition, right?
Yes.
So means this you didn't show the I didn't see the spectra comparing both of these structures, right?
This is the spectrum.
So the spectra are not very different.
No, and it's probably due to the fact that we only have one ligand on the surface, so we didn't get a huge redshift of the blue one, but we do see that the blue one is a bit redshifted.
Okay, but actually where you excite, it's mostly quantum dot transition, right? Which is just a little bit hybridization with a ligand.
So these are the oscillator strengths from around where they excite. And these are the states that contribute the most. And we see that although this is not the.
And this is based on VASP calculation?
Yes, because we could need to include Coulombic interactions because these are independent particle.
Approach, okay. Okay.
Okay. More questions 1. More questions 2. More questions 3. Okay, let's thank Levi. I would like to thank everyone for presenting, for supporting the discussion. The course was containing 3 components: methods, practical skills, and scientific communications. Also, everyone in this course has completed brief paper, and I think it will be a good appetite for computer-enabled research. Before we leave, and let's gather in this area and make a group photo with it. You may hold your just in front of screens.
How are you? Are you still with Sequence?
I moved to the physics.
Oh,
Guests are also invited to come and take picture. Please come, please come.
Are we gonna take it with that?
No, we can actually.
Yeah, for a while.
Why not?
I also took the quantum chemistry.
Oh, good, good. Please gather here, take some
Yes.
decoration. Come to the center. Yeah. Oh, please, would you like to join the photo?
I'm not belonging to this
You
class.
do, you do. You were participating in the discussion.
You are,
She could take the picture.
oh, Levi.
Oh, okay.
We have better camera.
Come to the center. Consolidate to the center.
Consolidate.
We're in frame.
No.
Okay, look at me.
Stand in the windows.
1, 2, 3. It's very slow. Okay. 1, 2, 3. Okay.
And do couple more just in case.
How to? Okay, I got back to the camera. All right. 1, 2, 3. Okay, that's pretty good.
Okay.
All right. Nice.
Thank you so much. And many thanks to everyone. So the meeting is dismissed. Everyone gets very ready for just coming and presenting.
I just
And
was
based
stuck
on
with
what
the
you
snow
did in
and
the forms,
everything.
there is a chance for
One was me.
even higher grades.
So you didn't drive?
No,
Took
I
some
didn't.
bus?
Yeah.
Oh,
From our building.